Hello everybody and welcome to CS302 Online, Week 10, Day 2 of coronavirus season and also the class. So let's see, we got 25 viewers now, that's much better. It's about 10 viewers like literally 30 seconds ago, so I was a little bit worried. So everybody can hear me good? How are we looking? You know, I don't actually need this on unless people join the Discord, so let's just leave that off. Yeah, sounds good. All right, cool. So we're not gonna put a head cam on until we fix some technical difficulties we had last time. We're gonna stick to the iPad. I think that's the general consensus for now. So all right, let's go ahead and get started then. Okay, cool. So let me move this over here real fast. Okay, so today we're going to be talking more about hashing, and I'll go ahead and refresh you on what we talked about last time, which is hash tables, hash functions, and we started talking about collision resolution, but now we're going to really jump into it. As a reminder, until further notice, classes will be happening at high noon, 12 p.m. Tuesday and Thursdays. So the next class would be April 7th at 12 p.m. Twitch mobile broken. Error loading content. That's scary. But you guys can see me good, right? The 25 of you. I guess on mobile it's having some issues. But yeah, we're good here. Okay, cool. So for until further notice, since I've had twice in a row, might have been 3 times, I can't remember. At least twice in a row I had problems with Twitch. With YouTube. We are gonna switch over to Twitch permanently until that fails, and as a backup we'll have YouTube. We do have a person on mobile being fine, so I guess you just gotta get a better phone. I mean, kind of a difficult situation now because everything's closed, but you know, but good, that's good to know. All right, so yeah, until further notice we'll stick to Twitch. I may try to experiment with WebEx. The problem that I have personally with WebEx is that it's very low resolution, and so it's very finicky and freezes a lot. So not a fan of it. It looks like I'm in the last decade trying to do like a web chat on like MSN or something. Even that was probably better than WebEx. But anyways, so yeah. However, I may do WebEx for the review for the test, because then you can have your cameras on and we can have one-to-one discussions. And I won't upload that one to the internet either. So that way you guys don't have your face on my channel. Yeah, it wouldn't work. Everyone's talking on WebEx. Well, I would mute everybody while I'm talking to avoid issues. Like that's what we're doing with the 301 and so on. But anyways, we'll figure that out later on. As is now, the test is supposed to happen 2 weeks from today. There was that tech test that was taken last time and it was available, and hopefully a lot of you took it. I haven't actually checked the statistics to see how many people took it, but yeah, that's how the test is going to run. We're going to have those file upload questions, which I might do for the majority of the questions, just because it gives you the ability to do more than just text. Because if I ask a question strictly with text, you're kind of forced to do that, and if you really want to do a diagram or something, you're limited. Whereas if I just let it be a file upload, you can just upload text, you know, write it in a Word doc, upload the PDF of that. However, you also have the option of drawing if you want along with text. So I think that's going to be the way to go. But anyways, that is how it's set up. Right now, the goal is to have the test on Thursday. Let me pop up with the calendar. Thursday, April 16th, in the range of time of 5 to 11 p.m. Where you would have a 3-hour time period to perform the test. That will vary slightly, could decrease, could increase, based on when the TAs take the test, how long it takes them to do the test, and then I'll multiply that by a factor of 2, and then you'll get essentially how long it takes. So I'm expecting the TAs to take anywhere from an hour and 15 to an hour and 30. Could be less though, but that's what I'm expecting, and then that would give you the 3 hours that you have. But if they get it done in 45 minutes, then, you know, the most you'll get is an hour and 30 minutes then, because that means that it's a really short test. So it's going to be strictly based on what what the TAs take for that. But that's going to be the time period that I'm expecting. If any of you that are here, the 27 of you, have a problem with having a 3-hour gap between 5 and 11, and by that I'm saying you would have to start the test to take full advantage of the 3 hours. You'd have to start the test at 8 p.m. so you have until 11. If you started after 8 p.m., you have less than 3 hours, which wouldn't be ideal. So get back to me if any of you have problems with that. I'm also going to make an announcement on Canvas and Discord, and if anybody has a problem with that, then we can try tweaking that, pushing it later at night, earlier. If we have a lot of people that have problems with it, then we'll stick to the default class times, which is people that are in the 8:30 a.m. class will take it at 8:30 a.m. People at 10 a.m. will take it at 10 a.m. People at 5:30 p.m. will take it at 5:30 p.m. of the Thursday or Wednesday of that week. So, but otherwise, everybody takes it at 16th. I would rather do that. I think it's easier for everybody, but I need feedback from you guys. So let me know. Also, give me feedback if you have any problems with the tech test, for those of you that did take it. And for those of you that missed it out, don't worry, it was very small amounts of points. We will have a worksheet. So what I ended up doing is I was going to give you 2 worksheets. One of them was going to end at AVLs, and the second one was going to cover heaps and hashing. I decided to just make one big worksheet, which should cover pretty much just about everything that would be on the test in terms of topics. Not every single possible question, but in general, the topics. And so that's what you're going to be getting on probably not tonight, but tomorrow night, because we finished hashing. And today's the last lecture that's going to be on the test. Potentially, maybe the beginning of the next lecture if I don't finish anything with hashing today. But that will be the last topic, hashing. Next week we jump into, I believe, graphs, and we'll save graphs for the final. So, all right. Anything that wasn't clear or anything? Otherwise, we'll hop right in. So, we're still having issues on. Apparently, some people have issues with mobile, but I guess they should just open the computer and try it then. Are you planning to? Here we have a question. Are you planning to have the TAs upload every answer as well when they're timing themselves? Of course, yes. I want it to be a real scenario. I want there to be them having to upload the test, them having in a situation like they would normally be taking the test, so in front of a computer. If they have, I don't know if the TAs have a way of drawing stuff or scanning or using paint. That's why I'm going to make both TAs do it. And yeah, so that way we can include that in the time it takes for them. You know, I might even get somebody who has coronavirus to be in the room just to increase the pressure, you know, so they're like, oh no, pressure. But no. But anyways, I will definitely make them do it like it's the real world. Are we going to get the answers back right away from the worksheet? So assuming that I give you the worksheet tomorrow, Friday, it's going to be due on the 17th, on the 10th, and then it's a week before the test. So if anything, I can go over the worksheet on review day on something like the 14th. And if not, then you can also ask the TA for answers. But most of those you should be able to figure out by just plugging into your program. Like if I make you do an AVL tree, you can check yourself by running your assignment 8, which would be an AVL tree, and then you can do that, right? That's also what I'm scared about when it comes to the test, because you can also just run your programs to do that, which is why I'm going to make sure that you have to put all your work in the test. So you don't just run your assignments to get the solutions to the test, right? You know, it's like I'm giving you ideas. But then again, you're CS. I assume that you've already had all these ideas and are trying to figure out ways to get the answers to the test, right? But, okay. All right, so let's jump right in then. Actually, let me drink some water. I was able to find some bottles this size. Okay, so the main goals today are we're going to review hashing, we're going to talk about collision resolution in detail, we're going to talk about different kinds of collision resolution, which are going to be linear probing, quadratic probing, double hashing, and then we're also, and I guess I didn't put it here, but chaining as well. And then if we get some time, we're going to talk about cryptographic hash functions, and that should be pretty much the day. So as a quick review of what we did last time, we said that hashing, you know, is when you don't care how the data is stored, you just want to be able to access it fast. So unlike AVLs of the things, you're trying to store data and retrieve it quickly. So you want to store some information like a phone book, and then you want to be able to access it quickly to use the information. You don't care the black magic that happens to be able to get that quickly and to store it. All you care about is being able to access it quickly, and if you want to modify it or delete it, same thing. So insert, search, and delete. And of course, the fastest you could do is O of 1, constant time. That's the dream, right? If you could do everything in constant time, then everything would be cool. Like, imagine you can just say, oh, it's gonna take me exactly 1 minute to pass this class with an A as long as I do this specific algorithm. And then you just do it and you're done, you get an A. But no, the world is not like that. When we talk about P versus NP, you see that it's definitely not like that. But anyways, so how do we do this magical hashing? Well, we do it using a combination of a hash table and a hash function. So the way it works is we have a hash, so we have an array, which is called a hash table, and we have our data that we're trying to insert there, but rather than inserting it directly, we pass it to this hash function that is going to take the value, which is usually some number or a string, is going to convert it in the hash function to a smaller string, and then use that as the index of the hash table. There is something known as perfect hashing, which is, or sorry, not perfect hashing, that's something else, but there's direct access tables, which is where you would, rather than trying to make the number smaller, you just take something like the phone book and then you just make that be the index itself, and then that's perfect because it's always going to be O of 1, but we talked about the whole cost of time with doing that. Perfect hashing, by the way, is when you're doing this mapping and every single value maps to a specific spot and there's no collisions or whatsoever. That's perfect because we have no problems, so that's perfect hashing. But anyways, I'll talk about it again later. I just threw a term out and I didn't want to freak you out. So here we have a little example of a hash table that I drew earlier because I was waiting for class to start. And so we have a bunch of data. We have 2, 8, 21, and 45. By the way, does the laser pointer still work? No, it doesn't work. So I'll just highlight like this. So we're talking about this. We have this data here. And what we want to do with that data is we want to store it in an array. And the way we do that is we feed that data to the hash function, which then takes that data, runs it to a specific function that we define. And in this case, that function is going to be modulus 10. Why modulus 10? Because we have 10 spots available, right? That's all we have available. And so we're trying to say, okay, we have 2, 4, and 5 items, and we're going to store them in 10 spots. They should all fit. Like if we do a hash function that is good, there should be absolutely no problem, no collisions whatsoever, because all the values are unique and we have more space than we need. In fact, we're going to talk about load factor. When we put all these in, as long as there's no collisions, we would have a 50% load factor, meaning that 50% of the table is full. That number is going to come into play later when I get to that. But anyways, so how does this work? Well, we take the 2, we feed it to our little hash function, which in this case is modulus 10, and 2 mod 10 is equal to 2, and therefore it goes in index 2. So the number 2 would go right there. Okay? So if you want to trace, it goes through the magical hash function, and then it gets put in there. Okay, what about the 21? Or here, let's do 45, so they're not all crowded. 45 also goes into our little magical hash function, which is mod 10. 45 mod 10 is 5. And then, oh snap, it gets put into there. And then let's do one more, which is 8. Feed it into that. 8 mod 10 is just 8. Goes there and gets stored there. And this is good because there's no collisions, everything is great. Okay, now that we have the data stored in there, let's try to access the data. So let's say we're looking for 21 in our data. So I went ahead and inserted all the numbers there. And I said, is 21 found in the data? So how do you access things in the hash table? It's kind of like the reverse. You take that, or actually not really the reverse. It's just a tweak of this, because rather than inserting, all we're going to do is we're going to check it. So you take the 21. So for example, when you inserted the 21, you feed the 21, 21 mod 10 is 1. You go and you put it in spot 1. In this case, however, we say 21, feed it in the same hash function as the insert. which is mod 10, which gives us 1, and then we go to that spot, and then we look at what's there. If that spot is empty, then we say 21 is not found in our data. So that's it. That's the end of that. If you're trying to delete it and it's not there, of course you say it's not found. But if it is there, like it is the case here, then at that point we can go ahead and delete it. And if we were to run 21 again, then it would be empty. So how do you delete something in an array, in actual implementation? Well, you could have a wildcard. You could just mark it as something. Or the way you could implement this is you could make this an array of pointers and they point to the object they're storing. And so then you can just set it to null. So either one of those will work just fine. What if you try to just look for something that's not there? That's the case of 99. As you can see, it goes to look at 9. There's nothing there. Yet again, that's pretty much it. How are we feeling? People are just saying it's fine. No questions so far. Okay, so that's of course kind of not exciting. It gets exciting when there's a collision. So let's say that we're inserting our 21, which we did, but then we're inserting a 51. 51 mod 10 is going to be 1 as well. And so what do you do in this case? Both 21 and 51 are trying to go into the same spot, but it's already taken. Oh, you know what, guys? I'm so sorry. I didn't bring the microphone close to me, so maybe I was a little quiet. Here's the microphone, by the way. So sorry about that. This should be much nicer. Hopefully I didn't kill everybody's ears. So, okay. This should be much nicer now for the audio. My apologies for that. Nobody said anything about audio, so ASMR. What's ASMR mean? I have no idea what that means, guys. Anyways, somebody post what that means because I'm curious. But capas. I know the kappa emote. But anyways, ASMR. ASMR. Oh, that stuff. Yeah, I've heard of that. Yeah, I have. That's, well, I can't criticize anybody's beliefs and things like that. But yeah, it's like, yeah, that's a good way of summarizing it actually there. Yeah, I don't believe in that, but, right, you know. Anyways, I can give an entire lecture like that if you'd like. So as I was saying, you know, we're inserting 21 and 51 and we have a collision. And so what do we do in case of that collision? Do we overwrite the 21 with the 51 or do we just not insert? Well, either way, when you teach your lecture whispering. But anyways, so yeah, in this case, what do we do in that case of that collision? Do we overwrite? Do we not insert? Well, either of those are bad because we have data loss. So, you know, we have a sad person for the data loss. What do we do? Collision resolution. So we have a happy person now. And so, okay, let's talk about collision resolution. So with collision resolution, happy person now, yes. So there's two main ways that we're going to talk about, and that is separate chaining or just chaining. And then there's also close addressing. However, separate chaining has other names. Sorry, I said it again. See, I told you I always have an issue with the names here. There's separate chaining, which is known as close addressing. And then there's open addressing, which is a completely different thing. Separate chaining and close addressing are the same thing. I literally have it right there. And see, I always get them flipped. So good, I don't know how to test. I will guarantee you that I will ask you to test that question, though. Because, you know, I want you guys to be better than me. So, yeah. Okay, so separate chaining is basically where we are, if you were here last lecture, is where we're going to, instead of just putting a single value in each spot of the hash table, we're going to make that its own little data structure, which could be a linked list, an ABL tree, or other things. Such as if you know what a B tree is, and it would be a B tree. I mean, you could put anything you want in there. You could just put it like a random ghetto array, but that would be kind of weird. Linked list is not the ideal because it takes over in time if you want to look around it. ABL is better because it takes log n. So let me ask you this. Here's a class question, and it's right here. Could we do a hash table here instead of like a nested hash table? So I'll come back to that question. You guys think about that. How about I show you an example of chaining first? So maybe I should have left some space here. So let me move this down here. You would think yes, need a separate hash function though. So a lot of people are saying yes, could you? All right, I guess the real thing I said is, how does it go? We were so occupied with the idea that whether we could, that we didn't stop to think if we should. That's really what we should be asking here. Should we do a nested hash table? Not could we do a nested hash table? You know, whatever that the meme is. But ideally, that's what I'm asking. You think that's going to be a good idea? Because I mean, you think about it this way. Okay, hash tables are O of 1, right? And we're saying that we have a collision. It takes, log n time with an ABL tree there. But if we put another hash table there, now we got two O of 1s. So O of 2, still O. That's constant time. So is that a solution for collisions? That's kind of the real thing that I want you to think about. So we'll come back to it in a second. I want you guys to think about that. But let me first show you a well-developed example of doing separate chaining. So let me go ahead and throw in some numbers here. I should have asked you for numbers, but I kind of want to have some collisions here. So I'm going to put in there 21, 33, 45, 11, 51, 22, 92, and then we'll take two more from the chat. How about that? You get to contribute two numbers. And then we got our hash table. Okay, so I guess the first thing you should think about when you're developing this is, okay, so we got 47. So the first two ones I'm going to take, 42 and 37. All right. I guess we'll take the next one. Why not? 69. Because it makes it an even even 10 numbers. Okay. I like having that 55 in there as well. I think we should throw in the 55 as well. Yeah, why not? Sorry, not 55. 5. That's because it's a big number, so it puts up a point. Anybody getting a lag? I do see a little bit of lag spikes. Could be cocks. Those cocks. But we're fine now. Okay. So, the first thing you should think about is, how big do you make your hash table? And furthermore, what do you make your hash function? So, the most popular thing to do for easy mode, school level hash function is modulus of the size of the table. So in this case, if we say, okay, one easy way to get this is just to take the first digit and do and use that as the index, which is the same thing as doing mod 10, right? So if we're going to use that method, then we can go ahead and make this an array of size 10. But if we wanted to do something bigger, which we'll maybe try later, then you could make it mod 15 or mod 20, whatever you want. Although, you'll see what happens when we do that. Okay. So for now, we're just doing mod 10. So our hash function is going to be x mod 10. And modulus is a really cool thing for hashing this kind of thing. It works great as a quick and easy thing to do. The tricky part is, of course, not all data is numerical. But, we talked about last time how to convert some stuff numerically, such as strings and things like that. Okay. So, we're going to go ahead and we're going to insert this. So how about this? I'm going to insert the first 5, and then for the rest of them, I want in chat for you guys to tell me what to insert them, okay? And since we're doing separate chaining, things are going to collide. That's okay. Just give me the index, and this should be super easy, I hope. So you guys do the rest. I'll do the first 5 in the meantime. So 21 mod 10 is just going to be 1. So because we're doing separate chaining, these are all pointers that are pointing to null in the beginning of this. In fact, to signify that, I can go ahead and put a little dot, which is what I used to do when I did linked list. Come on, chat. I said do the rest of them. So see how I do the first one. So I got 21. I'm going to put it here because that's where it would go. So in chat, I want to see something like 33 goes in 3. So I want you to do that for the ones after the line, starting with 22. Go. 2, 2, 2. There we go. Great job. Can see them. You guys are starting to get them doing. Good, good, good. That means you guys are awake and not just watching anime on the side, apparently. So, yeah. Okay. 33, as we said, would go here. And then 45 would go here. Let me zoom in a little bit so you see it better. And then I'm not going to draw all the boxes because it's too much work. But 11 is a collision, so we put it at the end of the list. And then 51 is a collision, so we put it there. And then for the rest of them, I'm going to see what you guys said. So 22, yeah, 92 and 42, they all go. That's right. Oh, wow, we put 3 of them together like that. So, yeah, so 22, 92, and 42, 37, 69. So this is rather simple. I hope you see that. And then 5, 5, 5, 5, 5. Okay. Joke's on you, I'm reading manga. I've never read that stuff. I'm not a fan of reading in general, so there's that. The only stuff I read are academic papers. Okay, so, all right. So we've inserted everything. Notice that out of the, what is it now, 12, I think? So 2, 4, 6, 8, 10, 11 things that we inserted. We had a collision on 1, 2, 3. So here, let me see you how I'm counting that. 1 collision there, 1 collision there, collision, collision, and collision. So we had 1, 2, 3, 4, 5 collisions. Okay, so we inserted 11 items, and we've had 2, 4, 5 collisions. And I guess you can say 1, 2, 3, 4, 5, 6. I would say like, okay, no collisions. All right, so that's not ideal. We want to have very few collisions, but it's not too bad because in the worst case scenario, what are the worst case scenarios if I'm looking for something in which 2 indices? I'm frozen. Am I frozen, guys? Because I see myself frozen there. That's kind of scary. Am I frozen? Good on my end. Okay, so I guess I'm just frozen. No, it looks good to me. Okay, good. Because like I could show you, I have the monitor here, and I guess because my download speed is so bad, my own stream is frozen. I wonder if I could lower the quality on my own thing to be. I don't know. I don't want to mess with it. It was frozen, but refreshing it fixes it. Yeah. I don't know what that means. Okay, so, all right. So, as I was saying, we have some collisions here, but in the worst case scenario, I think I'm going to try refreshing. Try refreshing. Or if not, it's okay if you're two behind. That's not too bad. Right now for me it's 12:28. So check your time. It was Frozen. It was a Frozen movie reference. Oh. Yeah, I've never seen Frozen. Imagine watching Frozen. Okay, so in the worst case scenario, if we're looking for something or we're inserting another thing that hashes to 1 or 2, those are the worst cases because those are the ones that are going to collide. So, if we're trying to insert just 1, the number 1, okay, so 1 goes in here, and then. Actually, I might have misled you there. If you think back to queues using a linked list, inserting is still going to take all of 1 time, even with a collision. Because what do you have to do that? You have the tail pointer, right? So you could have a little tail pointer there. Go back to this color here. Whoa, what am I doing here? Sorry, guys. I mean that looks kind of cool though. I'll leave it. But if we have a tail pointer and we're inserting 1. Then we just dump it there. Okay? So inserting into a separate chaining hash table is still going to take all of 1 time because we have a tail pointer. We can just dump it there. You could also... oh, wow, that's toxic. But okay. Anyways. Man, you threw me off with that. But okay, so I'm not, by the way. Anyways, here, even if we inserted it here at the beginning or at the end as I did now, it's gonna take O of 1 time to insert. So we're not losing speed on inserting. It's still gonna take O of 1 time to insert something into our separate chaining. However, if we want to access or delete, that's when it's going to take more time. In this case, if we're accessing something in index 1, it's going to take potentially up to 4, because once we've hit this index, we got to potentially, worst case scenario, we're looking for the number 61, which is not found. So we have to check 21, we have to check 11, we have to check 51, and then we have to check 1, and then we can say, okay, 61 is not found. Before that, we can't guarantee that. So now it's, I suppose, O of 4. But what that really can signify is the worst case. What is the worst case? Imagine that all these numbers ended with 1, and we use the same hash function. Next thing you know, everything is just one big linked list, and every other index is empty. That's O of n time, right? But of course, as I said, we could change this to an ABL tree. So suppose this was an ABL tree. How would that look like? Well, let's just do it for index 1. Index 1 would look like, I don't know, 21. Let's say that the ones here are smaller, 11, 51, and 1. And there, I mean, it doesn't look, because it's such a small tree, obvious, but this is now log n time. So now came back to the question that we were saying. What if this little subset of data, 21, 11, 51, and 1, if we use a hash function for that, where we looked at maybe the second digit, and if they don't have a second digit, we can just consider it a 0. Could we speed this up and still maintain O of 1, as the question asked? And so, would be like a nested hash table? And the answer is not really, because what you're doing in that case is kind of like double hashing, where you're saying, okay, take the first hash function, which is h of x, and then whatever that gives you, go ahead and hash that again using like a function g of x. You know, and it turns out that for separate chaining, it's not really going to help you much. I mean, nobody's going to stop you to do it, but it's going to still not be ideal. So most people in most real systems, if they're using separate chaining, they're going to use a B tree, which for all intents and purposes, just imagine it being an ABL tree. That's better, but ABL tree, just think of ABL tree. And that's your ideal. Again, none of this stuff is a problem if you think ahead of time and make a good hash function and you have perfect hashing, which is when you have no collisions. That's the ideal. It will cost the same amount of memory as just making one big hash table. Yeah, that's the other part. So that brings up a good point. And this comes back to the idea of load factor. And that is, if we have a lot of collisions, what can we do to kind of avoid that problem? And so the main thing that we can do is make our hash table bigger. And if we do the hash table bigger, though, we have to modify our hash function, because when you're making your hash function, you should never ever, I mean, it's bad that you have collisions, sure, we deal with it, that's what we're talking about now. But what you should never ever have in your hash function is that you feed a number, and what it gets you back is a value that is out of bounds of your array. Like, imagine it just gives you a negative value, or it gives you, well, I guess if it's Python, that's okay, you know, because Python negative values is just counting from the end of the array. But in C++, a negative value is going to crash the system, or a value that's out of bounds, it's just dangerous because it may crash the system. It's undefined behavior. You might get lucky and it's just inserting it into some scary spot in memory, but bad thing to do. You do not want to do that. That will get you the, where's the sad guy? Sad guy is gone now. Unknown location of sad guy. Oh well, sorry sad guy. You know, a little sad dude. So here, we'll just do another one. Okay? Yeah, rip sad guy. Who knows where he went? But anyways, I guess he was too sad. So, how do we do that if we resize it? If you just resize the the hash table, but you don't modify the hash function, you're never going to use those new spots. Because imagine I still use this hash 10 function and I make my array size 20. I'm never ever going to use spots 10 to 19. Never. Because the hash table doesn't allow it. The hash function doesn't allow it. So I wish I could just put the emote there. Oh, it's from that same person again. Yeah, I'm gonna get your IP address. Yeah. All right. So, anyways, it's a combination of resizing your hash table and modifying your hash function. If you're using modulus, which frankly, the best way to avoid this problem is just at the end of whatever magic you're doing for your hash function, throw in the mod in there and make sure that the number that you get out of that is fed to this mod to never ever have a situation where you're out of bounds, right? But yeah, if you do that, so if we go ahead and resize this to mod 20, do we really gain anything from that? Not with this data, actually, we don't. But if we have, oh no, we do, because we have a 1 here. So now this 1 and the 11 are actually going to hash to different spots. So it's going to ease a little bit this situation here. But that also brings up into the other idea of load factor. So there's a whole discussion on load factor, which I'm gonna post in the chat, and you can take a look, and then I'll post it on Canvas as well. By the way, I want to put the chat here so people can see it. I'll do that for next class. I forgot to do it, but yeah, check out that link with load factor. And one of the ways that you can avoid collisions is the more full your array gets, your hash table gets, the higher the risk of collisions, right? And ideally, if you have a function that uniformly distributes the data, then you shouldn't have collisions. But if it's almost full, then your risk is very high. So the moment that it starts to go higher into getting full, you may want to resize and decrease the load factor. And the load factor, I believe the formula is spots filled over spots over size of table. And if that load factor gets over like 75%, your risk of collisions is very high, and you have to rehash, they call it, which is make a new hash table. And you cannot, by the way, I should point this out, especially when you get your assignment. When you resize your hash table, do not, and I repeat, do not copy the data directly from this table into the other one and just keep going from there. You have to rehash, which means you have to take each of these values and then feed it to the new hash function, which will then store it in the new spot that it decides on the bigger table, which is going to be with a hash function that covers more spots. If you don't, the data will be lost. Because, for example, if we just copied and pasted this into another table, and then we're using mod 20, and we're looking for for 1, then we're not going to find it, because if we're looking for 11, we're not going to find it, because 11 would be in spot 11, but it used to be in spot 1. So now we're looking at 11, but it's still in spot 1, so you can't find it. So if you make a new hash table with a new hash function, you have to rehash every single value, which means feed it into your new hash function and store it in a new spot that it should be. It's kind of like if you remember when we were talking about queues back in the day when class was actually in person, if you remember those days, last decade. Imagine that in 2020 nowadays. But yeah, when we had class in person and we talked about queues, I made that issue that we were trying to figure out how to copy a queue into a bigger queue, and we just try to copy the array in a little for loop, and that would break it. No, you have to dequeue and enqueue again. So that it's kind of like the same here. You have to remove from this table and feed it into the new table with the new hash function. Okay, so now we had a question. Do you know what hash function does MDI use to be so broken? Oh, I don't know. I don't remember. I do know that ND5 checksum has been cracked now, and we'll talk about that at the end of the lecture when we talk about cryptographic hash functions. And I have actually a bunch of things here, and I might have some stuff on MD5s actually. So if I do, then I'll talk about it. You have Merkle diagram paradigm. Is that what MD stands for in MD5? So yeah, man, there's a big delay I think happening, based on the response of the chat. So, ooh, feels bad, man. I mean, I don't know. I could try to stop streaming, but that just sounds like a bad thing that's gonna happen if I stop and restart it. So, I'd rather not play with fire doing that. I guess if it's really, really bad. Okay, if it's more than 2 minutes, then I guess we should do that. I can give it a shot. You know, what's the worst that can happen? Class is canceled. Okay, so anyways, now you have a nice example of separate chaining. Now we're going to talk about open addressing. That's the other way of doing it. In open addressing, all elements are stored, as it says here, in the hash table, which means there's no linked list or additional data structures used. You still keep it in the array. But how do you do that? If you have a collision, you still have two things and you only have one spot. You can't just squish them together. Well, you're going to store them in other spots in the array. And that's what open addressing is going to be. And there's different ways to decide in what spots we're going to store it. So I believe I gave you a brief introduction last time, but if we have spot 2 and we're inserting the spots numbers 22 and 2, 22 goes there, you put in 2 in there, there's a collision there, where do you store it? What we're saying is, with open addressing, we're going to store it somewhere else in the array. Somewhere else. It could be here, it could be here, it could be here, anywhere. But inside of the array. Now, this is going to create problems of its own. We're going to talk about it slowly. We're going to start with linear probing. And all three of these are just ways of deciding where in the remaining of the array do we store it. So we have a couple of questions. What happens if you hash with floating points? Again, you have to find a way of converting those numbers into indices in an array. So if it's a floating point, you can use a floor function, a ceiling function. You could just use a specific decimal and use that as a hashing function. It depends, because like if you use a floor function and you have 22.5 and 22.6, bam, it fails. So it's really going to depend on your data. So if your data is like temperature readings of coronavirus patients who have fever, and you see that those temperatures are all between like 105 and 110. I don't know. Actually, that would be probably dead at that point. I don't know. I know it in Celsius. Let's say that their fever is like 38 degrees to 39 degrees Celsius. Okay. But they're all floating points because they're all like 38.1, 38.2, 38.56, and so on, right? If you know that your range of data is that much, it makes no sense to use just the integer and drop the decimal part of it, because you're going to have it all crash together. And I'll talk about it. That's actually a good example that we'll come back to in a second. But what you want to do in that case is maybe hash it on the decimal part, or other ways around that. So there are very cool hash functions that, even though you're feeding it two very similar values, they give you completely different spots. It's almost like it almost looks random, but it's not. It's pseudo random, and it's not. It's always defined where you feed it the number, and it always gives you the same number back. It's kind of how seed works in C++. Like you seed it one thing, and it gives you a really weird number, and you seed it the same number plus 1, and it gives you a completely different number. But there's a pattern there, and there's always going to give you those numbers based on that seed, which is why for randomizing stuff, you shouldn't be using random in the first place. But if you do, and you use seed, you use a specific time, because the time's always different. So then it's always going to be random, right? But what I'm saying is the same seed will give you the same random number. That's a really cool hash function where you can feed it two numbers that look very similar, and you can't figure out a way to differentiate it, but seed will take care of that. So there's people that have already figured that out. 110 fever, yeah, I don't know. That's why I should have said it was Celsius, because I know Celsius better than Fahrenheit. So, okay, so let's do an example of each of these. So let's start with linear probing. Okay, so with linear probing, let's go ahead and use the same numbers that we had before, actually. We might not use all of them, but it gives you a good set of numbers. And then we have some other stuff down here. Oh, and this is a reminder. Remind me, guys, to talk about the pros and cons of each of these. I mean, it should be kind of relatively obvious for some of them, but I'm going to give you a full list of pros and cons from Geeks for Geeks and other places that I have. So, yeah, before we end the lecture. That'll be the last thing we talk about, so, yeah. I think I answered already this question, but if not, repost it. Yes. Okay. Let's see how we're doing on that. Oh, it's not too bad. The delay is probably like 50 seconds, maybe 40 seconds. It's still bad, but not too bad. At least it works. YouTube was just dead. Okay, so with linear probing, the idea is as follows. We still have our hash function. You know, we can use our mod 10 again. But if there's a collision, we're going to store it in the next available spot. That's linear probing, which means if h of x gives you a collision, then try h of x plus 1. And if that gives you a collision, then try h of x plus 2. And keep doing that until h of x plus, let's say, m is equal to the size of the hash table. If that happens, think back to your days pre-corona of queues. Remember when we were talking about circular queue and we unqueued something and it was in the last spot of the array? What we did for the next spot is we just wrap around to the beginning and we start inserting from there. That's what you would do here. Same thing. If you're hashing and you keep looking for spots available and you run out of spots in the array, you go back to the beginning and you look for spots there. And that sort of wings the issue for now. However, eventually, even doing that, you're going to eventually wrap around. So suppose you're supposed to insert here and you start checking, you run out, you go to the beginning of this, you check. Eventually, you're going to hit again the spot where you started from. If in linear probing you do that, that is your sign that you cannot insert because, tell me chat, why is that? Why should I stop looking at this point if I hit the same value that I started with for the index? So I'm like, you know, so suppose that I have my, well, you guys figure that out. Full. Yeah, there we go. It's full. That's right. Yay. That's not too bad of a delay, actually. I assume it to be longer. That's right. The array isn't big enough. So yeah, if you keep inserting and you've literally collided everything here and you've reached the spot where you started from, it's kind of the same thing when your queue front and back cross each other. That's a sign that the hash table is full. And yes, as one person says there, you would have to resize your hash table and rehash every single value and so on. So that's going to be the limitation of this method. So here, let's go ahead and actually do it with the numbers. So bring these numbers down a little more so we can see them. Snap. Let me move all this stuff further down. You know, I prepared really hard today, I think. I don't usually write all these notes. Imagine not going impromptu every day. Not fun in that. Okay. So, okay. Let's make a nice box this time. You know, I feel like making a good box this time. Yeah, look at that. That's high definition box right there. And then let's just screw it up by putting bad lines. Can't get more screwed up than that. Whoa, that looks weird. Is that something you did intentionally? I wish I could show that. It's got the little like... Whoa, why does it look so... Oh, it's because I'm zooming that. It looks... I don't know how to show you this. That's weird. It's like trolling me. Hold on a second. I'll take a picture. Can you do this in Twitch or is this a glitch? Oh, you can't see it. It's like poking. Imagine not taking a picture of monitor when I can screen share. Take a picture and send it to Discord. Ah, so it is fixed now. So yeah, it was. I don't know. I'll just share it later. Or actually. This will be scary. I hope it doesn't explode. Oh, but you can't see it anymore. It was like semi-hidden. It was like this. Like you could only see the eyes right there of that. Like it was slowly poking. Oh yeah, I should have used snipping tool. That's right. Anyways, whatever. Imagine using not technology in a CS class. Okay, so moving on, because I wanna get through all the 3 examples of this, because you will do this in the test. You didn't do that on purpose. Yeah, but you can see it was like this. You could just see that part of the face. So okay, so we put 21 in. It goes here because we still have the same hash function mod10. You put 33 here, easy. 45 is easy. Okay, 11. 11 is our first collision. So we hit that collision there, and so we're using linear probing. And by the way, because art is expensive in terms of time, we're gonna... Did I copy that? I don't think I copied it. We're gonna copy that again because we're gonna do that 3 times. That one there, and that one there. Cool. Alt F4 for a screenshot. Yeah, that's not gonna work with me. Okay, so 11 is our first collision. So h of x is giving us 1 for that. So what we're gonna do is we're gonna add +1 to it. So that means that 11 goes here. Cool. Let's go ahead and throw in 51. This is where it gets nasty. 51, collision, gives us 1, +1, index 2, collision, +1, index 3, collision, +4, index 4, no collision, so we go ahead and throw it in there. Okay? You can see how things are getting nasty here. Yeah. Okay. All right. So, so here, I guess I should draw the pictures of what I'm doing. This is nice to see. So what's happening here is we'll use a different color for, well, why do I have 11? I meant 51 there, my bad. Okay, so what I did here is I went like this, like this, like this, and then we're good. Okay? So, yes. Okay. So, then we get 22. 22, we'll use green for that one. Would have gone here. And guess what? None of our numbers beforehand have actually used index 2 from the start, from the hashing. It's more of like garbage that didn't fit in the first spot, just kind of got thrown in. So 22 is like, yo, they took my spot. Now I gotta move, even though I would have been okay, you know, in the other method. Like I would have been Gucci, but now I'm not. I'm not Gucci. Not just that. It takes 4 comparisons to be able to put in 22. And so that brings us to exactly what our comrade here is asking, which is, so does searching for a value in a hash function using linear probing become O of n? Yes, it's going to be potentially O of n. And so that's the next thing that we're going to talk about. Let's actually stop inserting right now. We can insert the rest, but let's switch over to searching for information. Okay? So, and I introduced this concept last time. But here's the thing. When you're searching for something, the sign to stop is if you loop all the way around to the spot you started with, just like with inserting, you know that's full. Or if you hit a spot that's never been used. And now, be careful in my wording. Never been used is much different than was used and deleted. Let me give you an example of that. Suppose that I want to delete 33 from this hash table. Okay, that's easy. 33 mod 10 is just 3. I see 33. Let's delete it. In fact, a better way of marking that is just crossing it out, because you can't really delete things in a computer per se, right? You can mark it as empty. You can mark it as something. But here's the thing. Suppose you just mark it as empty or as never been used. Suppose now that I want to delete 51. 51 mod 10 is 1. So we go ahead and we hit 21, which is not 51. We check +1, we hit 11, that's not 51. We do +1, we hit potentially the 33 that is now empty. Here lies the problem. If we say, oh, that spot is empty, it means there must be nothing else, because otherwise, if there had been something else with a 1 in it, it would have gone right there because it's an available spot. It wouldn't have gone further, right? And so you can naively say, well, if there's nothing there, it means that it must not be there for the rest. And that's a lie, because 51's right there next. It just happens to be that something that used to be there is deleted. So how do we fix that? You have to add a special variable that's part of your little index, which is sort of a was used but is now deleted system. So you can say, you can mark it as was used at some point. Now this will work fine, because now you can say, okay, there's nothing here. However, it was used at some point. And because it was used at some point, it's possible that at the time when it was being used, the 51 may have been inserted and it had to skip that spot, as was actually the truth. And so now this will work just fine. You hit the next spot, you hit 51, and you don't just delete it, but you also want to make sure you have that marked. In fact, you can immediately mark those when you insert something, and that way, when you worry about deleting, you can just delete without having to worry about that. So I suppose how you do that, yet again, these could be pointers, pointing to the 21, pointing to the 11, and that. I'm not saying make linked list, just one pointer, and then you can just use null as the way to signify that it's empty. Or you can just add another variable here, and then just mark valid ones that are with a check mark, valid, 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 and so on. And you can probably combine both of these variables into one using powers of 2s to signify different states. So like, and then you can use bit shifting for that. So for example, you can say 2 means it's clean and never been used. 4 means it's currently in use. 8 means it was used, but is now empty. And 16, I don't think I haven't said yet, the fourth case is used and is not empty, something like that. And so you can easily check that by checking the different bits that are set, or just comparing the number using like an enum or something. So that's all implementation point of view. Don't worry, you guys can all implement this. This is much easier to implement than an AVL, frankly. You will have no problem with this assignment, right? Nervous, right? I hope so. Okay, so let's go ahead and try to look for the number 32. 32, let's use color blue for that. Would go here, but it is used. It's currently in use. So we got to check the next spot. While 33 is not there, it was at some point. So we got to check the next spot. 51, that spot is empty, but it was used. So we can't stop checking. We got to keep going. We go here, it's not found. We go here, it's not found. We finally hit here. This is a brand new spot that's never been used. That's when we can confirm and say, okay, guys, this was never used. You don't have to keep checking. All right. Last example, let me just show you how things can wrap around to show that it's full. So let's just keep dumping things in here. So let's say that we're going to insert a 92. Okay, what do we insert a 92? Chat, where am I going to put 92? In what index? Where am I going to put 92? 92 where? Dun, 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 dun. Ooh. No. I'm disappointed in those that are saying 7. Somebody said, why not 3? Why not? Exactly, 3. And now all of a sudden chat is changing its mind. Yeah, that's right. You put it in 3. Because 3, we have, it was used, and we have the mark that it was used, but it's currently available. And so, yes, 92 can just as well go there. Remember, we deleted it, but it's still available. And if we don't use it, we're wasting that space. So, blah, blah, blah. Excuses. All right. Well, then, you can redeem yourself by telling me, for those of you that said 7 before, where would you put 42 at? So those of you that said 7, there's at least 2 of you, 3 of you. Where would you put 42 at? 4. That's right. You have been redeemed. You're blessed. All right, cool. Now we're going to put in the 37. That one just goes there. It's all good. 69 goes here. 55 is going to go here. I'm going to skip that up quickly. And then let's go ahead and insert just a 1 in there. 1 is the really worst case scenario here for inserting. It's going to take n time potentially, right? It's going to go through everything. It's going to, I don't even know what color I haven't used it. Yellow. It's going to try to go here. It's going to keep going all the way. It's going to wrap around. And finally, it's going to insert it here. Same for searching for the 1. You got to go through the entire thing to find it. So now if I try to insert any number, doesn't matter what it is, any number. Let's say we want to insert a 24. 24 would try to go here. Check, 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 check. Back to where you started. Then you're like, yo, my thing is full. I got to make it bigger. Got to make a new fast function. So you could go ahead and make this of size 20 and then use mod 20 for that. And then it'll work fine. Okay. So here's the thing I want you to take away from this. I believe the name of this, and you know, when I do teach 219 semester 3, then I will know for sure if this is the right term or not. But I believe it's called Locality of Reference. I think that's the name. But let's forget about names and let me tell you what I'm talking about here. It turns out, and this comes back to the example that I was saying with the temperatures. If your data is clustered in your table, you know, linear probing is very bad because it has to work its way out of the cluster to store things. So imagine this. Imagine that you got 5 landfills and you got to find an empty spot in the landfill to store data. And suppose that one landfill is really, really full and you get sent to that landfill. Most of the garbage gets sent to that landfill. That's not good because you're going to take a lot of time to be able to figure out where to dump the new trash. You want it to be evenly spread. But if it's not, then if you do find a collision, you want to quickly get out of there to the next landfill, or at least get out of the area that's really, really full. And that comes around to this. What typically ends up happening when you have a bad hash function is that your data is not uniformly distributed. And I can kind of signify this using a graph. What you end up seeing is the following. You can think of this graph as your hash table, and this is sort of the usage. Okay? And so each of this range. This is like your range of the table, okay? You want to see something like this, which means it's evenly used up. However, you may find yourself with something like that. What that means is that this section of the table is more used up than this part of the table. Okay? And if I have to insert a number right here, and I'm using linear probing only makes me go this, or I guess because of the picture, it always makes me go this way. So that means I'm going to have to work my way with linear probing to find it right here. And now I can fill the spot there. So this is kind of going to slowly grow It's slow. I keep using colors that I've used before. It's slowly gonna push this curve up like this. In fact, if I want to kind of face it. Oh man, that's exactly what I was building up to say. That's that quote. But yeah, so it's gonna start up like this, and then it's gonna keep growing like this, and then it's gonna keep growing like that, and eventually, it's just gonna be like that. It's gonna get full. So what we're trying to do here is we're trying to flatten the curve, okay? And yes, somebody beat me to saying that. But yes, we want to flatten the curve, okay? So how do we flatten the curve, guys? Well, we flatten the curve by not going and making a group that just meets in one room and tries to take the test together, and then you get coronavirus in the entire room, right? That's why we don't want to cluster for the test taking. But anyways, in this case, the way you flatten the curve is we probe further away than the next spots available. We want to socially distance ourselves from the busy areas of the cache table. And so linear probing is not ideal because we're checking one at a time. Ideally, if we know that this area is like really full, then we just want to try to jump out as far as we can and hope that the next area doesn't have a big of a curve, right? So that's like, if you know that New York has a lot of coronavirus and you're trying to find an apartment there without coronavirus, then you want to try to not just probe and check that. Like you go here and you're like, hey, is this apartment coronavirus free? And they're like, no. And so you go to the next door neighbor. No. You're like, yeah, let me just try a block away. And if a block away doesn't work, let me try 10 blocks away, then 100 blocks away, then 1,000 blocks away, and bigger and bigger and bigger, right? Until you end up in like Alaska, where I think there's like that small amount of cases, and you're like, okay, I think I'm safe here. All right, so that is going to be quadratic probing. So that's going to be our next example here, quadratic probing. Quadratic probing takes, people said, okay, linear probing is not good because like, if we do a really bad job of hashing and we're just storing all the temperatures here, which we say are around the 37, 38, and 39 degrees Celsius, then there's going to be a lot of collisions in that area where the 37 hashes to, or the 38, if we're just using the integer. So how we're going to resolve this is we're going to go away from that area quicker. And so quadratic caching, the way it works is you start out by first hashing the first value using your hash function. And if there's a collision there, you start by checking the next spot, +1. So if this hash to 1, you can check. Or let's use 1 because 1's easy. Let's use 5 for that. If you feed in like a 55 into a table of size 10 or whatever, or actually this table says 100, I don't know, and you hash it and you get 55, okay? 5, sorry, not 55. Then you try the next spot, which is 6. Okay, 5 + 1. But then, instead of trying in linear probing, the next thing to try would be +2, +3, and so on. Instead of doing that, what you're going to do is you're going to take this I and you're going to square it. So the first time you try 5 + 1. The next time, because 1 squared. So 5 + 1 squared. The next time you're going to try 5 + 2 squared. And then 5 + 3 squared, and so on. So first time is going to be 5, just 5, then 6, then 5 + 4, which is 9, then 5 + 9, which is 14, then 5 + 16, which is 21, and so on. And as you can see here, in just 4 collisions that we had, we are checking 21 spots away from that. So that is like us, instead of hitting 1, 1, 1, 1, we're like check, 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 check. And maybe the 4th one is when we're out. Instead of having done maybe, let's say 17 checks before you got out. Can you see why quadratic probing is better to solve that problem when that happens? Chat. While you answer that question, I'm gonna make some space here. So this table is Here, we'll move all these guys somewhere up here. Yeah, that's good. Indeed makes sense. Good. I'm glad it does. Okay. So we're hitting close to the time here, so but we might not get to crypto hashing, but at least I'll get to the double hashing. So yes. Okay. So okay. So let's go ahead and actually put this to practice. So 21, 33, and 45 still get hashed to the same spot. The change is going to be when you hit 11. So with 11, it's actually going to go right here, because the first time that you hit with the quadratic caching, it's just going to be h of x plus I, but our I is 1. 1 squared is just plus 1, so it gets there. So nothing exciting happens there. With the 51, it gets more exciting. And I'll do the math here. So first time, 51 mod 10 is going to give us 1. That is a collision. Then we're going to try 51 mod 10 plus 1 squared. That gives us, of course, and I'm not going to put it again, the mod part, but this, of course, would give us 1 again, and 1 plus 1 is 2. That is also a collision. Next, we're going to try 51 mod 10, which is 1, plus 2 squared, which is equal to 5. 5 is also busy. Okay? So here you're thinking, oh man, linear probing would have put that in 4. This is not efficient at all. Well, this is like, you were like, oh no, there's a lot of coronavirus in New York, and you decide to move to Alaska, and you land in the one spot in Alaska, the one house where the guy had actually coronavirus. That's just unlucky. Can't do anything against luck there. That means you just were bound to get it. So, yeah. That's kind of the idea here. You know, you make a big hop, but you still got to land somewhere, and you can just get unlucky. So anyway, we go ahead and we try more. So 3 squared, that's 10. Okay, let's look at that. Well, we don't really have a spot 10, do we? That would be out of bounds. So what do? We just wrap it around. So spot 10 is actually spot 0 if we just wrap around, right? So then we put the 51 there. So let me bring up a couple of points here. It's very possible that when you do quadratic probing, here's the thing, with linear probing, if there is a spot empty in your hash table, then you will find that spot and you will fill it. So your hash table can be used up to a load factor of 100% if necessary. With quadratic probing, not the case. Suppose now that I'm going to insert, well, let's just keep inserting and see what happens. 22. Where's 22 going to go? 22 is just here, collide, then here, and then it's 22 plus 4, which is, or sorry, not 2 plus 4, which is 6. So 22 goes here. 92 is going to collide with that, collide with the 22 that we just put in. And then eventually it's going to be plus 9, which is 11. It's going to collide here. So we're going to have to try 2 plus 16, which is 18, which is here. So you can see here that you could make tons and tons of hops to get to find a spot. You could be hopping here forever, potentially. Suppose that, well, I think you should see the pattern here. Regardless of what we start with, suppose that we're inserting it like a number that ends with 0. Okay, so with 0, the numbers that you're gonna get that they can hash to are going to be 1, which is 1 squared, then 2 squared, which is 4, then 3 squared, which is 9, 16, 25, 36, 49, 64, 9 times 9 is 81, and then 10 times 10, which is 100, and then 11 times 11 is 121, question mark? I think so. Maybe, no, maybe 122. No, it is 11. 121, I mean. We're good. Okay. So, here's the thing. These are, of course, this is just spot 6, spot 5, spot 6. So can you see here how we're just wrapping in a circle eventually? We're going to be just going in circles. You have to find a way of stopping it. So sometimes some nice numbers will just keep bouncing between the same like 2 spots available. You know, it can get to that point when the number gets that big, right? Other times you may go in some strange pattern and so on. So you need to find a way of stopping it. So one way you can find a way of stopping it is after 5 or 6 collisions, you can be like, I give up, you know. There's 222s. Oh yeah, I meant to put in there 92. This is a 92 right here. Yeah. 13 times 2 is too much math. 12 times 2 is 100. So that's the next one, 44. So yeah. So which we've already checked that really. So you can, because it might be possible that you check things twice, but it doesn't mean you checked all possible spots. The best way to stop this quadratic caching is to just say like, yo, after 5 checks, I give up. Or after 20 checks, I give up. And so at that point, you need to resize this. And then you can try again. And so quadratic caching, you can guarantee that there's going to be a way to get out of this locality issue, but at the cost of making a bigger table. And for searching, you know, with linear, it takes O in time. With this, if you after 5 collisions you decide to rehash, then it can take 6 time, but that doesn't solve your problem. You might you could make the table as big as you want, but if you don't want to say wrap around as I did here, then your table will have to grow 5 times the size if you want to fit the 5th collision and so on, and that could be powers too. So what is that formula? Mod 10, I power 2 mod 10, right? Yeah. So keep it in balance. You use that mod 10 at the end, which is what I was saying earlier. So quadratic caching is not ideal. It's not the it's not the best thing to do. It's a solution to a problem that we don't want to have in the first place. So I highly discourage you from using this, but it exists and you should be aware of it. Any questions on quadratic hashing? And by the way, you could make it, instead of quadratic, you could make it powers of 3s, powers of 10s, whatever you want. Which brings me actually to the last one. Ask questions if you have any with quadratic caching. Otherwise, I'm just going to quickly cover the last one since we're out of time here. The last one is double hashing. Can we solve this with prime numbers, a prime size table? So yes, that's something that I was going to get to if I had time at the end, but I didn't. So one of the things that, at least when I learned hash tables, they recommended me to do is make your hash table the size of a prime number. Because when you're doing mod of a prime number, there's less chances of collisions because it's a prime number and the way prime numbers work. There's no way to divide it into any other number than itself. So remember what prime numbers are. It can only be divided by the number itself or by 1. And so suppose that and here's the thing, because of the formula that somebody else said, which is like, you know, x mod 10 plus I squared, and then you mod 10 again to see where it goes. Because you do this mod 10, this internal mod could be whatever you want it to be. But here's the thing, if I do x mod 5, and then I do x mod 10, these are not ideal because whatever is 5 and 10, like those are multiples of each other, you're gonna have the same issues. The good thing about a prime number as for your table size and your modulus is that prime numbers by default there's no collision, there's nothing that can divide by them, and so there's less chance of you getting collisions. So ideally, if you want to take anything away from doing the ghetto hash functions with modulus, is you should make your tables the size of prime numbers, and just if you need a rehash, go for the next bigger prime number. And then there's less chances of collisions that way than just picking an arbitrary number. So did you read that somewhere, or did you actually figure that out yourself? Because part of me suspects that you just read it somewhere, which is okay, but I'm curious now. So how do we prevent that problem from existing? What problem? I don't know what you're talking about, so follow up on that. But anyways, last thing here. Double hashing. Double hashing is like kind of what we were talking about earlier
with a hash inside of a hash table, except instead of putting a table like with chaining, we're going to put it in here. So we tried linear, which is just +1. We tried squaring it. And then double hashing is just expanding the concept into whatever your custom probing is going to be. So if you would like to do probing in a fashion that is not quadratic, but maybe powers of 3s, or you want to have a specific math formula, like you want to add always 3 to that, or maybe you want to add 3, but then the next time you want to add 20. You want to have a very, very, very specific formula for doing that. That's double hashing. And that means first try h of x. And if there's a collision, then feed that value to another hash function g of x. And then if there's a collision there, then feed that value into g of x again. This, however, is a little dangerous because if you do that hash function wrong, so it's not really going to take advantage of the space, or it's going to waste a lot of space. So, it's not very popular, but it is there. So I wanted to make you aware of it. So if I decide my hash function is always going to be +5, my second hash function, then if I have a collision for, let's say I'm inserting into this example here, the 11. The first time there's a collision, I say +5. Okay, 1, 2, 3, 4, 5. Then 11 goes there. Whatever you do there, you have to do the same thing when you're searching. All right, so now let's see the questions. I have vague memories of being told to use prime numbers to hash a long time ago when I first started CS. Yeah, okay, so there you go. So yeah, so yeah, ultimately now you know. So I could always follow up on this next time, but I said yes. One tip that they usually tell people when you're actually implementing a hash table and you want it to, ideally you want to do something smarter than modulus, but if you are just going to use modulus, make your table sizes the size of prime numbers, because when you're doing modulus of a prime number, it's not going to give you similar values when they're like multiples of that number as it would between like mod 2 and mod 4, because it's a less chance of a collision basically. Okay, so just to summarize, hash collisions are something we want to avoid, but that we should be able to manage. I recommend that you do, and a lot of libraries implement the separate chaining method. That's just better because you don't. The problem with the other probing methods is you got to probe around, and that's going to be O of n time. That's really bad. If you can just create an ABL tree or something, you can never do worse than log n time. And remember, if we want to be safe, we could use an ABL tree for everything. It's log n, insert, search, retrieval, deleting, anything, access, whatever. The reason we're using hash tables is because we want to achieve that goal of O of 1. And if we're going to sacrifice that when we're trying to hash into a table like with probing, then what's the point of using it in the first place? So I recommend that if you are going to use a hash table, that you use it with chaining. And that's really, I'm going to test you in the other ones, but that's what I want you to take it out, which is why I spend more time in that. But ideally, to avoid collisions in the first place, remember, uniformly distribute the keys so that each position is equally likely. And that's a very hard thing to do. And here's the thing. Don't make your hash function so hard to compute that it's amazing. It's like it never has a collision, but it takes 10 days to compute. Because then, where's the efficiency? All this time that I've been saying O of 1 time, I'm hand-waving the fact that you have to compute the hash function. Yeah, a little modulus calculation isn't going to hurt anybody, and it's not going to take that much time, but it does take a little bit of time, right? And so don't just hand wave that in the real world. You want to make that hash function efficient to compute, easy. Okay? And so the last to mention, and I guess if you got to go to another class, that's okay. You can catch up this later. But these are some nice things to know, is some of the advantages of each method, okay? So the advantages of separate chaining, which is the one that I preach. It's simple to implement, which I think you guys will appreciate, if anything else, when you do the assignment. It never fills up. You never have to resize the table if you don't want to, because if it happens to fill up, the chains just grow. But the table itself can stay the same size. It's less sensitive to whatever hash function you give it or load factors, because again, you got the chain side. And the best time to use it, and this is from Geeks for Geeks, is When it is unknown, how many and how frequent the keys may be inserted or deleted. So if you don't know how much you got to put in and remove, that's just going to be the safe way to go. The disadvantages of it, so not everything is the cure to everything, is cache performance of chaining is not as good, as the keys are stored using potentially something like a linked list or an AVL. Open addressing provides better cache performance as everything is stored in the table, and so you can load a specific part of the table in memory. Now we're talking like a real hash table that is so big that you can't fit it on like L cache, and we'll talk about caching in 2.19, but you got hard drive is really slow, RAM is fast, but even faster than RAM is cache. But your cache is very limited in the computer. You might have only 4 megabytes of cache memory, and there's different layers of cache, and really it's just memory that's really, really close to the actual CPU. And it gets to the point where like the fact that RAM is far away from a CPU, and I know you're saying, oh, it's here and here. Yeah, no, this distance, like speed of light is actually something we will actually talk about in 2.19. It's a hindrance for us. We need speed of light to be faster, actually. But because of that, cache is really, really close to the CPU itself. And so this is much faster to work with than this. With open addressing, you can load the table here, and it's much faster than trying to dereference something in RAM, which is slow. But that just means implement your algorithm better so you load cache better. So I don't think that's a big disadvantage. Also, I suppose you technically do waste some space with chaining. Like you can see here that index 8 was never used. You know, it wasn't ever used, but sure, why not? Linear probing is the one where you're like, if you really want to use every single piece of memory available at the cost of access time. But then again, I still disagree with that. And there's a little bit of extra memory for the links themselves, I suppose. Just like they're in an AVL tree, like the pointers themselves, they have memory, you know. So there is a cost of that. Load factor is number of slots in hash over number of keys inserted. So I was right about that. And then finally, quadratic probing lies between the two in terms of cache and performance and clustering. So if you want cache advantage, linear probing, because it just goes to the next spot available to search. If you want sort of middle ground, you do quadratic. If you do the double hash function, you lose that ability of caching because the computer can't predict where the next big jump is going to be to. At that point, you might as well use separate chaining. And I'm going to go ahead and post this table, which is found on the open addressing section. So you can read that on your own. And if you have any questions, you can ask me next class. And so next class, we'll talk a little bit about crypto hashing, maybe for the first 20 or something minutes. And then that'll be the end of the content for test 2. So keep updated. I will go ahead and post a worksheet online tomorrow night. And I will now, this is the official end of the lecture. We went a little bit over, but you know, so be it. Please feel free to ask me questions now. Otherwise, I shall end the lecture. So question time. Any questions? Let's see. I'm watching the stream, so I'm still talking there. So big time delay now. Okay. What's the difference between open and closed addressing? So open addressing is where you're not defined to a specific address for a hash, which is the one where you do probing. Closed addressing means you stick to the index that you were given by the hash function, which means you have to use chaining to do it. So closed addressing is separate chaining, yes. I don't know why I have such a hard time messing that up. When you think about it, it makes sense. But when you say it, I don't know. It's just one of those things that's never going to go in. Feels bad. I'll put it here to remind me. Talk more about this next time. And then crypto hashing. we'll talk about security and hash tables for a little bit. That won't be on the test, the second crypto stuff, but it's interesting stuff, I think. The second question I'm going to, it was irrelevant. Don't worry about that. All right, I guess I could type a message because there's no delay in there. Post questions. Nobody on the chat, either on Discord. Can you give a summary again of what you wanted for assignment 9, please? Okay, that's a good one. So assignment 9, wait, when does assignment 9 due? It's probably due pretty soon, actually. If I remember, probably like this weekend. I don't know. Check whatever Canvas says. That's fixed. We're not delaying that one. But that's an easy assignment, to be honest with you. But assignment 9, you're given data. You're given an array. You have to heapify the array, which means using that array in place, you make it a heap. Don't take everything out and put it back in. No. Because I want you to actually learn how to heapify things. And then, once you've heapified it, you're going to insert the last two non-dynamically allocated variables, which is the FMB and the JSquad. And then you put them in. And then when you put them in, of course, put one at a time. That's when you got to insert it at the end of the next variable spot in the complete tree. And it's got to bubble its way to the right spot. It's probably not going to be at the top of the thing. So don't panic if those are the first two things that, those are not the first two things that come out when you start taking things out. But anyways, after you put them in, then you're going to go ahead and start deleting one at a time. And as you delete it, you're going to print it out. You may deallocate it at that time, or you may wait to deallocating until after you're done deleting everything. And then the last thing you do is you deallocate. The trick with deallocating is FMB and JSquad are not going to be in the same spot at the end of the array. So you're deleting for that to avoid memory leaks. It's a little bit tricky because when you delete, you got to check to see if what you're deleting is JSquad or FMB, in which case you don't want to delete it because they're not dynamically allocated. So you want to skip that. So it's a little bit tricky, I suppose. But I had a lot of messages that people were confused. So it seems most people are saying that the assignment is due on Sunday or Monday. So yeah, double check Canvas for the real time of that. But that is a fixed deadline. So cool. Other questions? Still got 30 viewers. If no more questions, then that's it. I'm gonna head to UNO. I'll be here for Q&A, maybe half an hour, and then I will head over to UNLV for the first time since the Monday of spring break, because I gotta get a photo taken and I gotta go pick up a. Remember that I had problems with the Apple Pencil? I ordered another one. It finally arrived, so I'm gonna go pick it up. I'm gonna take some bleach, just dump it on bleach to make sure it's disinfected since it's coming from China. Probably, and then we'll have a backup pencil, so that's a good thing to have. So yeah, wish me luck in I'll try to be very safe to stay alive for you guys. But if I was to catch corona, I'd probably record the video, so if I die, you can watch them and still finish the class. By the way, keep posted about the S and U stuff. Nothing has been 100% defined. Just keep posted on your emails. I'm assuming that they're going to iron out what the details are. But I think the biggest question right now is if you take an S for the class. They've announced that what I had predicted and known already, which is a D- would be considered an S. Which brings up the question now, can you use an S to fulfill a prerequisite? So if you want to take 326 next semester, you need 302 for that. Or at least 37. I think you need 302 for that. Here's the thing, you need a C or better to get into those classes. If you take an S can signify D-. It could also signify actually an A. I mean, I wouldn't recommend you switch it to an S if you do that. But nobody knows whether they're going to accept it or not. And that does not have an effect on your GPA. So what I was thinking and what I said is like, okay, there might be people that get a C because of the circumstances. C for circumstances. And they take the S because of their GPA because they may lose scholarships. But still, they would have qualified for 226. But now because they have an S, do they qualify or do they not? And that's what everybody needs to figure out. And that's something that the big people apparently are going to figure out. But they've asked for input, so we're all giving input, and that's why we had the discussion in Discord. So nothing has been defined. So people tell you like this has been decided. It has not been decided yet. All that's been decided is that you can switch your grade to an S or U after the semester ends. So which means just work your way to getting a C or better if you want to pass the class. All right, let's see what the final question. So why is it not a good idea in separate chaining to just use another hash table to obtain all one time potentially? Because you can just make you can combine both hash functions and make a bigger table, and you would get pretty much the same efficiency as that. And you wouldn't have and you wouldn't lose anything in that sense. S has no effect on GPA. I'm gonna pass component. Yeah, so I don't know. I think frankly though, the good news is if you fail the class, if you get an F in the class, then I see no reason why. I mean, maybe you were. By the way, drop date is like happening, I think this week or next week. So be on point if that's you. I hope nobody drops, but life happens. But yeah, if you're beyond the drop date and you get an F in the class, you 100% want to switch it to a U because it will not affect your GPA, and you probably have to retake the class anyways. But at least in the current time when you retake it, it won't affect your GPA, which means you won't lose your scholarships. So that's one thing for sure that is good in general. But I hope none of you are in that situation. All right then, I will try to take a picture of that as well, of the setup. All right then, so if no more questions are there, I'm on Discord chat right now, so switch over there or write me some questions. Again, I'll be there until 2, and then I will. Thank you for the good for the Godspeed wishes, because I will need to. I'll try to take a picture of the strip since I'm gonna drive down Flamingo. So who knows? Maybe I can do a new background. All right then. So let's switch over. I mean, this background's nice too, right? All right then. Thanks for watching, guys. Get your assignment done. Keep posted on the worksheet. I will give you guys probably 2 days, 3 days to do it. So you might end up having assignments 9 and the worksheet due around the same time. Again, keep posted on Discord. If you haven't joined Discord, then you should. I don't know. I hope everybody's on Discord. And stay safe, everybody. I'll see you guys.